many, or if not most, transmission line engineers will use to model noise, corona discharge. I think next several of me, I'll just keep talking. Okay. Grounding rods, stray voltage and electrical safety. What grounding system design will be used, and what engineering studies and standards inform this design? Yeah, that's a pretty dense question in terms of like what all is informed by that, but I think to just like make it a useful answer to that question is that grounding is a large component to this project for many reasons. Kind of like starting high, and we can dive down as needed. Each structure will have its own dedicated grounding, and that's a function of the ground resistivity, and we will have the numerous field tests that will let us know what that needs to look like so that all grounding is, everything is sufficiently grounded, because you have to have that as part of your base design, right? And so this particular system has communication with the 161 infrastructure in this local grid because that 161 kV line is an underbuilt component to the greater structure. And so why is that important? Well, each one of those 161s has a direct communication with the substation at 10 to 20, 10 to 30 mile intervals. And so as part of the engineering assessment and electrical studies component of this project, they will go through and execute a coupling study to make sure that we don't need to change additional grounding on that 161 system at the substations as well. That will all be a part of this CapEx. The engineering studies, that's part of the overall engineering process, like identifying those grounds. There's also a maintenance component, an operations component that will include grounding studies. So if anybody has more questions on that, we can keep diving into it. What soil resistivity testing was performed along the route, and what studies support ground rod placement and depth decisions? So that's basically what I just addressed. Like before we can finish up a structure install, we'll need to know what the grounding requirements are, and that will be determined through field-based soil resistivity. We don't do that until the route is finalized to minimize, iterative exercises. Typically, no issues, having sufficient ground based on whatever soil resistivity we encounter. What research evaluates step and touch potential risks near towers and grounding rods? And that's going to roll back up to the NESC. There's a couple other codes evaluated that are, inform that as well, but there would be no touch risk at the structures because of each structure will be grounded. Number 36, what studies address stray voltage risks to livestock, pets, and humans? Okay, so stray voltage, what does that mean? That's the E and the EMF, so an object existing at a voltage has a mutual coupling phenomenon with metallic objects within close proximity, so like a barbed wire fences. We kind of talked about that a little bit on the EMF section, number 6, questions 22 through 25. As part of the NESC requirements, there's a thing we call like clearances, what are the required clearances, and so if anybody's maintained electrical infrastructure, there's minimum there are approach distances and all kinds of clearances that are informed with that. Well, this particular clearance has to do with like equipment proximity, and then it even rolls up to things like barbed wire fences and overland agriculture infrastructure that's metallic. And so this project will make sure that we have sufficient grounding on all impacted metallic infrastructure, so that there is no risk to livestock operations, human health and well-being and safety, and that is pretty strictly defined by NESC. There's, again, some other codes that kind of roll into there as well, but that is another parameter that informs the height and size of these structures as well. So many of the mitigants or tools in the engineering toolbox is distance, which again, we think of the 161 size compared to the 765. The stray voltage component, it informs directly the height of the structures. Okay, moving on here. Number 37, what research evaluates interactions between grounding systems and buried utilities, wells, fences, and drainage tile? So that does kind of fall under the greater EMF study as well. That's within your corridor of interest, where you're going to go through and make sure you don't have any mutual coupling risk for induced voltage, which will lead to that, the stray voltage component. And I guess I should circle back on the stray voltage. That's often conflated with an induced voltage. So transmission lines exist at a voltage regardless of power flow. You can have a mutual coupling component that can have an induced voltage in metallic objects. That is often conflated with stray voltage. So stray voltage is actually more on the distribution side, and is not a direct cause from transmission lines. That has to do with like a distribution grounding system. If you got insufficient ground due to port thermal, electrical resistivity or ground grid placement, there's a whole, it's a very deep rabbit hole to go down on the stray voltage side of things, but our main focus is within that corridor of impact. We will make sure that any induced voltage on any metallic infrastructure is below the required NESC induced voltage requirements. So the buried utilities, wells, fences, and drainage tile. So there's a parallel facility study that is another component to what I've been rambling here about on the induced voltage component. Like if you've got a distribution line in close proximity that parallels it, that would be a candidate for additional grounding on this project, because you could expect some minor induced voltage. Same thing with fences and overland. Irrigation equipment, so buried tiles, depending on the material, drainage tiles. So if it's non-metallic, we're not going to worry about it, just as the physics aren't there to have an interaction there. But anything metal, we're going to evaluate. So as part of the project, you do a SU, subsurface utility engineering, and that would be understanding what's below this line, and that is SOP for design to make sure that you've got required grounding, and if there's any additional cathodic protection that would need to be added, that's all on the project. And we would do that anywhere the line travels. Okay, number 38. How will grounding components be mapped and disclosed to landowners, and what best practice studies support this approach? Starting in the end and working backwards, the best practices, again, these are mostly design code driven for the industry writ large. And in this instance, your ground rods are going to be at the structures connected at each leg on the foundation, as required based on the resistivity of the ground. We don't expect ground grids, so that would be more of a substation or a static equipment install. If we did have a situation where there was a ground grid installation, that would be within the fence. That would be confined within the fence of that infrastructure. So I can't think of a scenario where we would want to have those underground components mapped and logged to be communicated to landowners, because they're not going to exist other than the ground rods of the structures. I mean, if that was the case, then we would have them marked compliant with any safety code requirements. This is a good one. 39. What corrosion and long-term performance studies support grounding material selection?